So previously in this course, we've been looking at just one single random variable at a time. For example, it might be a binomial or a Poisson or a geometric random variable, or it might be a random variable for which we've written down its probability mass function, but we've just been dealing with a single random variable. Now in this section, we're going to start thinking about what if we have two or even more random variables, how should we look at them together? And we're going to start this by looking at an example. And our example is this one. We're going to toss a fair coin 3 times, and X will be the number of heads in the first 2 of those 3, and Y will be the number of heads in all 3 of them put together. So the first thing is to say is that we know how these random variables work individually. For example, we know that X is binomial 2.5 because we're tossing 2 coins, each of which is heads with probability 1/2. So we know that its probability mass function looks like this. It can be 0 or 1 or 2 with probabilities 1/4, 1/2, 1/4. That just comes from our normal binomial distribution. Similarly, we know that Y is binomial 3.5 because it comes from tossing 3 coins. So its probability mass function can take the values Y equals 0, Y equals 1, Y equals 2, or Y equals 3. And if you calculate what the right binomial coefficients are, the coefficients go 1, 3, 3, 1. So this becomes 1/8, 3/8, 3/8, 1/8. So those are the probability mass functions. Now, when we've got more than one random variable hanging about, and we want to emphasize that a probability mass function only refers to one of them, we use the phrase marginal probability mass function, or marginal distribution, where marginal means it's only to do with one of the 2 random variables. So that first table is the marginal distribution for X, and the second table is the marginal distribution for Y. But where there, marginal just means the normal probability mass function we know and love. Now, it's all very well to look at them individually, but X and Y are based on the same set of coin tosses, so we might be interested to see how they behave together. So if we want to know how they behave together, we use something called the joint probability mass function. And the joint probability mass function tells us what's the probability that X is one thing and Y is another. So the joint probability mass function takes that notation. And that's telling us about what's the probability that big X equals little x and big Y equals little y at the same time. So this is telling us about how the 2 things interact together. So if we want to write down joint probability mass function, we need to write a table with all the possible values. So Y can be 0, 1, 2, or 3, and X can be 0, 1, or 2, and we can put in here the value, the joint PMF. So it would take a little bit of time to work these out for yourself, and I'm going to write them in quickly and invite you to work them out later. But for example, for X and Y to both equal 0, that requires all 3 coins to be tails, so that's 1/8. For X to equal 0 and Y to equal 1, that needs tail, tail, head, if you think about it, because then the first 2 have no heads, but the first 3 have 1 head. So tail, tail, head has probability 1/8 again. And you can fill in the table. I invite you to check the working here yourself at leisure. But it's not too difficult to work out that those are the probabilities. Now, for normal probabilities, we had that for a partition AI, that is A1, A2, and such, you might remember we stated this result, that the probability of some event is that you sum over all the bits of the partition. But we can do the same with random variables, right? Because the set of x equals x for x in the range of x, that is a partition. Right, because x has to take one of the values in its range, but it's only going to take one of the values in its range, so that's what we called a partition. So the same result as we had for probabilities, for a probability of events, gives us that we can write the marginal distribution for y as a sum over the partition given by the different values of x. Or in probability mass function notation, that's this. So in other words, to get the marginal distribution out of the joint distribution, you have to sum over the variable you don't care about. To get marginal from joint, sum over the other variable. So if we think about what that means for our table up here, this means if we want to calculate the marginal probability that x equals 0 from this table, we need to sum up this row, and that gives us an eighth equals a quarter. So if we put the sum over there, then this is the kind of probability x of x. And similarly, we can sum over the x equals 1 row to get the probability x equals 1. That was a half, and that row comes out as a quarter. And if you check that with what we had for the marginal distribution up there, a quarter, a half, a quarter, you'll see that we've got a quarter, a half, a quarter here as well. That, incidentally, is why it's called the marginal distribution, because we end up writing it in the margin of the table, like this. Similarly, this works with x and y swapped over. So to get the marginal distribution for y, we have to sum over the values of x, which means summing down the columns of this table. So if we put py of y here, summing down this column gives us an eighth. An eighth plus a quarter is 3/8. A quarter plus an eighth is 3/8, and an eighth is an eighth. And you'll see that that's the same as the marginal distribution we had there. So again, we got the marginal distribution by summing down rows or columns of the joint distributions table. So that was about just two random variables, but you might have lots of random variables together. But in that case, everything basically works the same way. So for multiple random variables, x being a vector x1, x2, ... xn, the joint probability mass function works the same way. It's probability x of x, or if you prefer, the probability x1, x2, ... xn of x1, x2, ... xn is just equal to the probability that all the x's take those values. X1 equals x1, and x2 equals x2, and x3 equals x3, and xn equals xn. So that's just the same thing, but if you've got n variables instead of 2. And in just the same way, you can get the marginal distribution from summing. So if you wanted, say, the marginal distribution for x1, px1 of x1, then that you have to sum over all the other variables. So you have to sum over x2, x3, x4. So this would be a sum over x2, x3 up to xn. So obviously we don't sum over x1 because we want to leave that in our marginal distribution, but we have to sum over all the others. So whether you're dealing with one random variable or many random variables, you can show how they interact through a joint probability mass function. And you can get the individual marginal distributions out by summing over all the variables you don't care about.